Electric current. So that one is problem number 3. The Coulomb's law is an equation that we came up with in your Coulomb's law lab so that you know. Ohm's law is what we're going to come up with today, so you can fill that out when we're done with the lab today. But you still need to know what the individual variables are, which is current, and the definition is the rate of flow of charges. That's what you're writing into your vocabulary sheet for number 3. The rate of flow of charges. When you think about a current, generally we use it in the terms of the current in a river, right? How fast the water flows or how slow the water flows. So the rate of charge flow is very similar to the rate of water flow in a river, except this time it's the flow of electrons rather than water particles. So you can think of those water particles as electrons. I'm just going to go into more detail about charges, but this is the main definition right here. The other thing I want you to include in this is the fact that we use I, capital I, to represent current in our equations. We already used capital C for Coulomb, so we had to think of another variable, and I was the one that the scientists came up with. So, I is your variable for current in your equation, and A is the unit we use, which is amperes. So that's the unit for current. If you say that your charges travel at 100 coulombs per second, you can say it travels at 100 amps. So amperes, or capital A, or amps for short, is your unit for current, which is your definition for number 4. Question. Yes. Ooh, wrong one. Now I got to move it beside it. Okay, so as I stated, another representation of amps, again, is coulombs per second, because coulomb is your unit for charge, and it's how fast the charge flow over time. It's a rate, and we're going to be measuring current today with, this is actually a voltmeter and an ammeter. Ammeters measure current. Voltmeters measure voltage. I actually added that as number 10. Ammeters and voltmeters measure current and voltage. I don't have the definition, but it's pretty obvious from the name, right? Resistance. We're going to work with some little resistors. They look like this. And the meaning is very straightforward because it is a device that allows, a device that resists the flow of current. So it's going to slow electrons down as they travel through your conductors. A good analogy that I like to use is traffic. When you're driving through the highway, you can go at a pretty high rate, a pretty fast current if you're an electron, but then when you hit a toll booth, you hit some resistance. The resistor is like your toll booth. These cars are like your electrons. They want to flow at a high rate, but something is slowing it down. Your light bulbs, or any appliance that you plug into an outlet to get electricity, those appliances and that light bulb is a resistor. But the resistors we're going to use today are going to be these little guys right here. So this is which one? Number 5, resistance is the tendency of a material to resist electric current passing through it. So it just slows things down. Another analogy, and I'm going to provide these slides to you, so if I'm going too fast, you can always access these later. But another analogy I like to use is water pipes. So first of all, I like this analogy of a water tank above the ground because you can think of voltage as storage for energy. So you've got for example, a battery, and I'm just going to draw it this way because it kind of matches the image that I have here, that stores tons of electrons at the positive side, and then it has this area that wants to gain electrons, but it can't gain electrons unless there's a pathway. This is like your positive side of your battery. It stores all the electrons together, but those electrons want to repel. Just like this water wants to move down the pipe. Now, your wire or your pipe is how the water travels, and actually it's a very similar analogy because the wider your pipe is, or the wider your wire is, generally, the faster your current can flow. The skinnier your wire is, or the skinnier your pipe is, the slower your charges can flow. And so, the resistance can also be based on the size, the width, even the length. If you had a short wire, obviously the charges are going to flow a lot faster versus a really long wire where it's going to take more time for the charges to travel. So the other analogy, I've got tons, is like a straw. If I asked you to drink a glass of milk and there was a competition, would you choose the thick straw or would you choose the skinny straw? Thick, obviously. Would you choose the short straw or would you choose a super long straw? Probably the short straw. So that's how it works with current and conductors and resistors. So another way of creating resistance is to bottleneck your conductor. You add resistance is a bottleneck analogy, but all of these analogies come down to the point that you need a voltage, some sort of potential energy, storage of electrical energy, and then you need a pathway, and the current is going to encounter, the pipe is going to encounter some resistance, but in the end, that resistance creates work. And when we're talking about circuits, like our circuits the other day, the work it created was light, or if it's attached to some sort of machine, it's going to create movement or kinetic energy. So that's the type of work that we end up with when we are working with electrical circuits. Voltage is what we use to represent our energy storage, our potential energy, and then obviously as we use up energy, we end up with a low potential energy source. So this is our high potential, and then once it reaches the end, we've got low potential. So I've got all these analogies that I'm giving to you. One thing I didn't mention, I should have added this to the slides here, is we've got another symbol called ohm. It's our omega symbol. And this is our unit for resistance. You're going to need to use this you're going to need to recognize this when you get to your lab today. So, ohm is a capital omega, which is your unit for resistance. That is number 6. Okay, you're going to need to know this for your for your concept builder tonight. So, what relationship did you guys get for voltage versus current? Can anyone tell me what the relationship was or what the graph looked like in general? Linear, right? Did anyone not get linear? Few. I had one group, only one that did not get linear. So you noticed one steep slope, and maybe they were on separate graphs, but together they look like this. What relationship, what thing popped out at you about the results of your graphs? Can anyone tell me what the results represented? Shouldn't have been hard. Alec? The resistance. So the slope for this one should have been about 33 ohms, because ohm is the unit for your resistance. And the slope for this one should have been about 100 ohms, which is why you had to do the percent error to see how close it was. But ultimately, your slope is equal to the resistance. So in order to get Ohm's law, we want the general equation for this graph here. So we're going to go y equals mx plus b. B basically went through 0. And your y, remember, you can't keep y's and x's the same. It has to represent your graph. So y represents voltage for V. Slope represents resistance, which is R. And then slope, and then x represents your current. Again, this is one you need to memorize. Current is represented by I. This is Ohm's law. So what was the most obvious relationship? Because your homework is on proportions. Velocity, how is it related to current? What is the proportion between velocity and current? As one increases, the other decreases? Increases, right? That's this relationship. As current increases, voltage increases. All right, let's look at other aspects of this. If I were to increase voltage and keep current the same, so this doesn't change, how does resistance have to change to make this equal? If I increase voltage, how would resistance have to change? Thoughts? It's not hard. Sit. It's an increase. This is another direct proportion. Okay, let's do this. If I kept voltage the same and I increased resistance, what would the current have to do to make sure the voltage doesn't change? If I increase resistance, what would the current have to do? Decrease. So this is the only inverse proportion. The resistance is inversely proportional to current. So when you do your homework tonight, if the current increases by 2, voltage increases by 2. But if the resistance increases by 2, current decreases by 1/2. And it's a direct inverse, not an inverse squared. It's just simple division. Any questions on proportions? I feel like you guys are pros at this right now. No? All right. The other homework, I know a lot of you already did it, but you're supposed to do worksheet, the reading worksheet, which is replacing your notes, 3-4-2. And then we have a quiz on Thursday of next class on Ohm's law. So the practice you're going to do for homework tonight is going to help you with that, and then we're going to do a worksheet next class.